Hello, I am Deepan Chakravarti Padmanabhan. Today I will be presenting our work Leveraging Shape Information in Few-Shot Learning. This is a joint work along with Shruti Gowda, Elahe Arani and Baram Zunus. Few-shot learning techniques address the practical challenge of learning artificial intelligence models in limited data scenario. FSL methods aid AI models to learn quickly the necessary skills to generalize on novel tasks with less direct supervision than the conventional training strategies. The major challenges in FSL is learning generalizable robust features because the models tend to overfit to the limited training examples. In FSL setup, the challenges of deep neural networks in the conventional data-hungry training setup is further exacerbated. One of these challenges include bias towards the textural patterns. The model, rather than concentrating on the global semantics in the data, it concentrates on the textural patterns. Finally, learning shortcuts in the data such as class-specific color correlations or color schemes in the data or any statistical regularity in the training data that is not standard to the real test scenarios. All these possibilities restrict FSL performances. Therefore, the objective is to develop an approach to address texture bias and shortcut learning in the FSL setup. On the other hand, we humans excel at learning with limited data. We quickly adapt to new situations while remaining both precise and robust to changes. Various cognitive neuroscience studies report the utility of prior semantic information gathered by infants and adults to recognize objects. Therefore, in this study, we leverage the prior knowledge already implicitly available in the data as a supervisory signal to help few-shot models learn the intended solution. So the solution here is, inspired by cognitive biases of human, we inject prior knowledge to FSL models in form of shape awareness. This shape bias addresses the texture bias in neural networks and aids in learning robust global features for few-shot learning. The proposed approach LSFSL developed shape-aware FSL models by leveraging the implicit shape information present in the RGB input image. This negates the need for an additional dataset to instill shape awareness to FSL models. During training, we learn a dual network architecture comprising of RGB network, which takes as input the standard RGB input image, and an additional shape network which extracts and leverages shape information from standard RGB input. The shape network takes as input an image with enhanced shape semantics. This shape image is obtained by employing Sobel edge operator to the corresponding RGB input image. The initial stages of an RGB network and shape network employs a deep neural network based feature extractor followed by a classifier. The two networks are trained in synchrony utilizing latent space feature alignment and decision alignment objectives to distill shape information to RGB network. The decision alignment and feature alignment is bidirectional. As we noticed, shape network requires certain texture information from the RGB network to improve generalization and vice versa. The feature alignment utilizing mean square error objective enhances the feature space of RGB network by distilling meaningful shape information from the shape network. This ensures that the earlier stages of the RGB network is more shape aware in the representation space and are unaffected by changes in color schemes and perturbations. The decision alignment using KL divergence objective enhances the decision boundary and RGB network is less susceptible to color schemes and perturbations. The alignment objectives regularize both networks and addresses overfitting to trivial solutions. In addition to the alignment objectives, the standard supervision loss cross entropy is used to improve the generalization of both networks. Therefore, the overall loss for pre-training or the meta-train training stage of few-shot learning includes both the cross entropy losses for each network and the feature alignment and decision alignment losses. The meta-test training stage includes only the pre-trained RGB network to extract robust generic features. The extracted features are used to train a simple classifier such as a logistic regression or learn class-wise prototypes for the nearest neighbor classifier. In meta-test test stage, the pre-trained RGB network and the simple classifier which we trained in the meta-test training stage is used. We evaluate the few-shot performance of a baseline FSL model trained using the LSFSL approach. The FSL model performance is the RFS baseline model which employs a ResNet 12 backbone followed by fully connected layer. As highlighted, the shape awareness aids in achieving a performance gain of 1 to 2% over the baseline model, as well as various other state-of-the-art methods across all benchmark FSL datasets. In addition, FSL baseline model containing ResNet 12 backbone and trained by leveraging the shape outperforms methods having WRN 2810 backbone, which has 3 times more parameters than the ResNet 12. Unlike humans, deep neural networks strongly depend on local texture information to recognize objects. To test the impact of learning shape semantics on texture bias in FSL, we evaluate the models pre-trained and meta-test trained with mini-ImageNet images on texture-biased query images. We randomly select a texture from available texture pattern images and transfer the query image with texture transfer strength ranging between 0.1 and 1 as shown in the top figure. As shown in the results below, LSFSL trained models demonstrate that the shape semantics learned help the network look beyond the local texture features and consistently outperform the FSL baseline model, that is the RFS method which we chose. Training data collected in real-world scenarios include various inadvertent superficial cues. Deep neural networks tend to learn the class correlation with these cues and illustrate limited generalization. We test the ability of LSFSL models trained with shape awareness to resist learning superficial spurious correlations by analyzing the generalization across 5 different scenarios of tints, such as tints to only the query set in the testing stage, or tint to only the support set, tint to the pre-training stage images, or tint to the pre-training and query, and tint to pre-training and support set. An example of class-specific tinted images is shown in the left-hand side image. The table on the right side illustrates performance under increasing levels of spurious correlations introduced through class-specific tints arranged from left to right in ascending order. We observe that shape-aware LSFSL model significantly outperforms the corresponding baseline without shape awareness in all scenarios, even in the extreme scenarios of spurious correlations as shown in the last 2 columns. Humans rely on high-level abstractions and structure in the data to recognize objects, whereas deep neural networks tend to learn statistical regularities that affect generalization in challenging test scenarios. We test the impact of distilling shape as an inductive bias on the susceptibility to statistical regularities by evaluating query images after applying a radial low-pass Fourier filter at increasing severities, as shown on the left-hand side image. This filter preserves the visible high-level abstractions for human recognizability, but introduces a superficial statistical regularity by removing high-frequency component. The graph on the right-hand side shows that shape-aware LSFSL models are less susceptible to statistical regularities than baseline models that lack shape awareness. Therefore, the shape awareness introduced by LSFSL models confronts the vulnerability of deep neural networks to learn shortcuts and takes a positive step towards the human perception of processing high level and structural information to recognize objects. Input image perturbations imperceptible to humans result in adversarial examples that affect the generalization of deep neural networks and compromise the integrity of intelligent systems in safety critical real time applications. This immensely challenges the desired scenario by many users, which is to develop robust classifiers using only a few training examples. We studied the utility of shape semantics as an inductive bias in generalizing to adversarial examples. The query images are perturbed using the square black box attack at multiple perturbation strengths. As the figure illustrates, across various perturbation strength, the shape-aware counterparts of the baseline FSL method are less prone to adversarial attacks due to the high-level shape semantics information learned in the feature extractors. We illustrated earlier that incorporating shape information using LSFSL approach increases the generalization and robustness in various few-shot settings with RFS model. The model RFS is trained using a non-meta learning based few-shot method. To evaluate LSFSL utility with meta-learning based approaches, we considered adding LSFSL to frequently reported prototypical networks. It is clear that we improve performance as illustrated on the mini ImageNet dataset and reduce susceptibility to learning shortcuts in the form of color cues as illustrated in the tinted mini ImageNet dataset results. Thus, it is evident that our approach can be extended to both meta-learning and non-meta learning based few-shot settings. The susceptibility of deep neural networks to texture bias and spurious cues are particularly detrimental in the few-shot learning paradigm compared to conventional learning scenarios. To address the vulnerabilities of few-shot models, we proposed LSFSL approach that incorporates shape semantics as an additional inductive bias. This enhances both the generalization performance and robustness of few-shot learning models. We demonstrate the compatibility of our pipeline with both meta-learning and non-meta learning based few-shot learning approaches. Therefore, incorporating meaningful inductive biases can further improve learning deep neural networks in low data regimes. Thank you. For further questions, please contact us.